Welcome back to Lockdown Math. Today we are going to be talking about logarithms in kind of a back to the basics sort of lesson. The intent is for someone who maybe is not familiar with logarithms yet, or who has seen some of the rules but has been confused by them. And as always, to kick things off, I just want to get a sense of where the audience is at right now. Because I have a couple suspicions, but I think doing a live poll to see where everyone is might be helpful. So if you can go to 3b1b.co/live, which you can find the link in the description, and you can also just follow the link that's up on screen here. You'll find a poll, and at the moment it asks, what best describes your relationship with logarithms? A, I've never heard about them before, or never learned about them before. B, I've learned about them but sometimes get confused by all of the properties. C, I understand them but wouldn't know how to teach them. And D, I understand them well and could comfortably teach them to someone else to make them understand well too. So we've got a good split. This is good and interesting. Like I said, the intent for this is to create a lesson that I can point people to in the future if they're just not comfortable with logarithms, and I want to be able to say, oh, here's a place that you can go for how I think, how I think you could approach it intuitively. And for those who are in the camps of, let's say, understanding it but not knowing how to teach it, I think there's an interesting meta question around logarithms, because I was scrolling around a couple teacher forums before doing this particular lecture, and when people ask, what is the hardest topic to teach in high school math, in the sense that students seem to have trouble with it the most, logarithms is one of the most commonly indicated answers, which is interesting. And I can guess maybe it's because there's a ton of these properties that you end up having to learn. So if we skip ahead of where we're going to go, you've got all these piles of rules that just look like a bunch of algebra that can be hard to remember and easy to kind of mix things up in your head. And I think when people have, these sort of nightmarish recollections of what high school math was like and what logarithms did for them, it's often those particular formulas coming to mind. And what I want to do today is try to talk through, one, how to think about them, but also just on the meta level of if you're teaching somebody algebra, what are the points worth emphasizing? What's the way to get it built in their intuitions? So let's go ahead and see how people are answering on this one. We've got a pretty even split between three possible categories. All right, so the most common viewer right now answered C, that they understand them, but they wouldn't know how to teach them. The second most common are those who said they understand them well and they could comfortably teach them. So this is sort of revealing that, okay, the existing audience on the channel at the moment, it's people who are into math and they're going to be pretty comfortable with logarithms. And then after that, B, people who are confused by some of the properties, and then at the bottom, people who have never learned about them. Now, if you watching are one of the people who answered A, that you've never learned about them, or that you're not comfortable, keep in mind, this lecture is actually meant for you. So when we're doing some live quizzing, and we're going to have an answer on here, and we're going to have people, answering probably pretty quickly, probably correctly, given that, as you can see, most of them are coming in comfortable with logarithms, don't let that be intimidating. Don't let that be something that indicates you should be answering quickly, or you should necessarily be getting the right answer, right? So I think the most intuitive way to think about logs, if you're just going to start off, is to say, at a very high level, logarithms are something that can take in a power of 10, and it just spits out the number of zeros at the end of the number. It does more than that, as we'll talk about, but just at the very high level, this is getting a sense for what they do. And I think it's pretty important, because what you're saying here is, hey, look, as we walk from 1 to 10 to 100 to 1,000 to 10,000, each step we're multiplying by 10. The output of the log of that value, just steps up in these increments of 1. So you could think about this as saying, when I plug in a number to the log, if that number happens to be a power of 10, I'm just counting the number of zeros. What's log of 1,000? Oh, it has 3 zeros on it. What's log of 1,000,000? Oh, it has 6 zeros on it. It's the zero counting function. And I think you can get yourself very far in terms of understanding various properties of logarithms just by thinking in the back of your mind, okay, when I plug in a power of 10, it's a zero counting function. I plug in a billion, how many zeros are at the end of a billion? And these numbers are all very intuitive to us. We see them in the news, we anchor our intuitions in terms of how many digits does a number have, and logarithms are just capturing that idea. And in fact, logarithms have been of particular interest in the last couple of months. What's kind of interesting is if you look at this Google Trends chart that's just looking for logarithmic scale, okay? People searching for the term logarithmic scale, you'll notice, there's kind of an ambient interest sitting around in September of 2019 up to February of 2020. And for some reason, suddenly there's a strong interest in understanding logarithmic scales from the general public. I wonder why that is. And we see this sitting around early March or so. And of course, this is because this is when the corona outbreak was really starting to kick into high gear, and everyone wanted to understand exponential growth. And a common way that exponential growth is plotted is with what's known as a logarithmic scale. So I actually made a video about this, and in it, I was, creating some animations and wanted to illustrate this idea of exponential growth. And the main idea here, I'll go ahead and skip back to a different animation, is if you're tracking the numbers, in this case, this was the number of recorded cases of COVID-19 outside of mainland China in the months leading up to March, you could just track what the absolute number is, but the pattern that you'll find is that as you go from one day to the next, you tend to be increasing multiplicatively. It's a little bit like earlier, we were seeing the powers of 10 one step to the next. You're multiplying by some amount. The way that the virus was growing was very similar. From one day to the next, you're multiplying not quite by a constant, but in this case, for this sequence of days, it was around 1.2 in that region. You're multiplying by something. So when you're plotting this, it ends up looking like this classic exponential curve that curves upward. And that can sometimes make it hard to see where it's going or what the overall pattern is. So a common trick is to say, instead of looking at this y-axis that increases linearly, as in here I'm going from 5K to 10K, 10K to 15K, 15K to 20K, each step is additive, we're adding 5,000. Instead, use a y-axis where each step is multiplicative. So you're going from 10 to 100, 100 to 1,000, 1,000 to 10, 10,000. All of these are increases by multiplying by 10. And what you could say is the y-axis is now plotting not the total number of cases, but the logarithm of the total number of cases. And this actually makes it kind of easier to see on a plot if you wanted to project out what that trend would do. And it's a little bit of a naive model to say, oh, it's going to grow exactly exponentially. But in the early phases of something like this, that is what it is. So I kind of fast forward in the animation I made for that video. And what's interesting is if back then, I think I posted it on March 6th, if you just found a line of best fit and you stretched it out and you said, when is that line going to cross 1 million? Which, because the y-axis is growing with multiplicative steps, each time that you step up, you're multiplying by 10. So even if it might seem like the 20,000 cases or so that it was back then is very far from 1 million, when you understand logarithmic scales, it actually didn't seem that far. It was only 30 days away if you naively just drew out that line. And in fact, fast forward to around April 5th, which is when that would have predicted we hit 1 million cases outside China. That's pretty much the day that it happened. I think plus or minus a day, I don't remember exactly, but it was right in that neighborhood because I remember thinking, wow, it was kind of a naive model for the video to even use, and it's shocking that it matched so exactly. Thankfully, since then, the growth has stopped being exponential, so if you look at it on a logarithmic plot, instead of going up in a straight line, it starts to taper off. But point being, anytime that you're coming across something in nature, or even in a man-made construct, where what's natural to think about are multiplicative increases, logarithms come in to help you. So let's go ahead and think about what these actually are. How are they defined? Okay. And actually, there was a question asked on Twitter right before we started that I think hits this very perfectly. So Max182 asks us, addition's inverse is subtraction. Multiplication's inverse is division. But I never truly understood if exponentiation's inverse was nth rooting or logarithms. If either one could be, if either one could really be called that way, can they? That is such a fantastic question, Max. And I think it comes down to the fact that with addition and multiplication, you're not, or I'll just draw it out for you, actually. This is going to be easiest. If we have some kind of exponential relationship, let's say 10 to the power 3 is equal to 1,000. There's 3 different numbers at play here. We're showing a relationship between the 10, the 3, and the 1,000. And aside from writing it with an exponent, there's 2 other ways we could write that same relationship. We could also say that the cube root of 1,000 is equal to 10. This is asking 1,000, what number raised to the third is equal to 1,000? That's sort of what the cube root is asking. And another way that you could phrase the exact same thing is to say the log base 10 of 1,000 is equal to 3. Okay? 3 different notations, the same exact relationship. A while ago, I made this video about an alternate possible notation that would center in the idea that you think of this relationship between the 3 numbers with a triangle, where you'd have our 10 sitting down here, the power sitting at the top, 10 to the third, and the thing they equal sitting to the lower right. And whenever you want to talk about a function or an operation between 2 of these numbers, you indicate which one of them you're leaving out. So to write 10 cubed, we would include the 10 on the lower left, the 3 on the upper right, and then we leave out that bottom one. So this is indicating that we're taking a power, 10 cubed. For that radical, what you would say is, we know what's on the bottom right, something to some power equals 1,000. We even know what the power is. Something cubed equals that 1,000, but the thing we don't know is on the bottom left. That is the sense in which radicals are an opposite of exponentiation, where if the thing you don't know, instead of being on that bottom right, is on the bottom left. But what logarithms are, it's an inverse in another sense. Because what it's saying is, in this triangle relationship, we know the base, it's 10. We know the power that it should be, 1,000, but the thing we don't know is what's in that exponent. So to answer your question maybe even more briefly, we could say that 10 to the x, the inverse of that, the inverse is the log base 10, of y, of some other variable. Whereas if you're taking x to the 10th, some unknown raised to a power, the inverse of that is going to be the 10th root of some other value. And on the triangle, it's basically asking which of the things do we consider to be a variable? So are you considering that lower right to be a variable quantity? Are you considering that top to be a variable quantity? And what is the unknown? But I really liked this idea of making explicit how we have 3 totally different notations for the same exact fact. One of them you're using relative positions of the numbers. One of them we introduce a new symbol, this radical. And one of them we introduce a new word, log. So these 3 syntactically different ways to communicate the same idea seemed wrong. And so I made this video about, an alternate possible notation. And while I don't necessarily think that, we should teach logarithms with this triangle, because convention is what it is, so it's better to start getting people used to the usual expression. What I do like about it, and starting off with it, is when you see and think about this triangle, it's really emphasizing that what the log wants to be is that exponent. Every time that you see log of some value, you should think in your mind, okay, whatever this number is, it really wants to be an exponent. It wants to be an exponent. And we'll see more of what that means as we go on. Okay, so every time you see a log, it wants to be an exponent, this value 3. And more specifically, it should be an exponent sitting on top of whatever that base is. Now, in terms of convention, for the first part of this video, I'm just going to be using log without a base written on it to be the shorthand for log base 10. Because log base 10 will be the most intuitive thing out there. You should know that often in math, the convention instead is that log without anything might mean log base e. There's also another notation for that, ln, for natural log. We're going to talk all about the natural log next time, so don't worry too much about that right now. And there's also yet another convention. Often if you're in a computer science setting, log, without any added sugar to indicate what it is, defaults to meaning log base 2. So this can sometimes be a source of confusion, but it basically depends on what discipline you're in. In math, not moth, math, people really like a base of e. We'll see why next lecture. In, I'll say engineering, but really it's anything where you want good intuition with our normal base 10 number system. Log means log base 10. And if you're curious, often in computer science settings, log base 2 comes up all the time. So, like I said, in the back of your mind, if you're trying to think of some of these properties, just resting on the idea that log counts the number of zeros at the end of a number, that can get you a really far way. So we're going to start going through a couple of these properties, and I want to do this just with a set of practiced examples. So we'll transition away from the poll, and this time to the first proper question. And the question asks you, which of the following is true? A, the log of 1,000 times x is equal to 3 times the log of x. And remember, we're using the convention that it's base 10 log. B, log of 1,000 times x equals log of x cubed. C, log of 1,000 times x equals 3 plus the log of x. D, log of 1,000 times x equals 3 to the power of log of x. And E, none of the above. Okay? And remember, like I said earlier, we should fully expect that all of those people at the beginning who said they understand logs well, they're going to be answering immediately, they're going to be answering correctly. But if you're someone who doesn't, don't let that intimidate you. When you're looking at a problem like this one, what I would encourage you to do is just plug in various powers of 10 and think in terms of the idea that the log function counts the number of zeros. Okay? So I'll give you a little moment to think about that. Great. Okay, so I'll go ahead and grade it. And as always, if that's faster than what you're comfortable with, know that it's only because I want to proceed forward with the lesson. So in this case, the correct answer comes out to be log of 1,000 times x is the same as taking 3 plus the log of x. Okay? And now let's think about that for a moment. And like I said, when you're just getting started with them, I think the best thing to do is just be comfortable plugging in various numbers. And the best numbers to plug in are the ones that are already powers of 10. So if you're asking something like log of 1,000 times x, well, I don't know, let's just plug in something for x. Log of 1,000 times 100. Okay? Well, we know how many zeros are going to be in the final answer here. Well, 1,000 times 100 is 100,000. We already intuitively have this idea that when we multiply two powers of 10, we're just taking the zeros, the 3 zeros from that 1,000, the 2 zeros from that 100, and we're putting them next to each other. So it should be 5 total zeros. But if you really reflect not just on how did the number turn out, but why did it turn out that way, it was the 3 zeros from that 1,000 plus the 2 zeros from that 100, which we could also write by saying the number of zeros in 1,000 plus the number of zeros in 100. So this idea that a logarithm of the product of two things is the sum of the logarithms of those two things, in the context of powers of 10, that's just communicating what's already a super intuitive idea for a lot of us. If you take two powers of 10 and you multiply them, you just take all of their zeros and kind of cram them onto each other. So the way I've written things out here, it's actually indicative of a slightly more general fact, which is going to be our very first property of logarithms, which is that if we take the log of a times b, it equals the log of a plus the log of b. And now anytime you see one of these logarithm rules, if you find yourself, squinting your eyes or you're a little bit confused by how to remember it, just plug in examples. I'm being redundant, I'm saying this a lot, but it's because I think it's very easy to forget once you're swamped in the algebra itself and you're sitting on some kind of test and it's just got a lot of symbols, to remind yourself you are okay to just plug in some numbers. That's a fine thing to do, and often it's a great way to yield intuition. So in this case, saying log of a times b and breaking it apart, we could just think, oh, that log of 100 times 1,000, which is 5, there's 5 zeros in it, breaks up in terms of the number of zeros in each given part. Great, wonderful. So carrying that intuition further, let's try another practice problem. And again, if you know it, great, you'll be able to answer it fine, but maybe think not just what is the answer, but how would I explain this answer to someone? Or how would I try to get a student to come to this answer on their own without me having to tell them what the answer is, right? So there's two potential audience members. There are those who are interested in the lesson itself, and then those who are interested in the meta lesson. So our question asks, again, which of the following is true? A, log of x to the n is equal to n times log of x. B, log of x to the n is equal to log of x to the power n. C, log of x to the n is equal to n plus log of x. Or D, log of x to the n is equal to log of n times log of x, or none of the above. So again, take a moment to answer. As people do answer, we'll start to see them roll in. And if you are struggling to think of where to even start, just plug in some powers of 10 and see what intuition you might get from it. All right, so it looks like just about everybody is landing on one particular answer. Hopefully it's the right answer. Like I said, all to be expected. So let's go ahead and see if our majority ended up correct. And they did. So the correct answer here is A, which it looks like 4,000 of you got. Congratulations. Telling us that log of x to the power n is equal to n times log of x. So again, let's say that you're trying to teach this to someone, or if you're trying to come to grips with what it means yourself, I think a fine place to start is plugging something in. And in this case, for log of x to the power n, let's just try it with 100 to the power 3. And you could try it with other ones to see if the patterns you're doing actually work. But if you're thinking it through, not in terms of simply seeing what the answer is, but trying to think of why the answer turned out that way, sometimes one example will do. Because 100 cubed, we can think of that as taking, well, that's 3 copies of 100, right? I'm taking 3 copies of 100. And when I multiply all that out, and I think of log as counting the number of zeros, we say, oh, it's going to be some number that just has 6 zeros on it. That's what it means to take 100 times 100 times 100. I can just think of grouping all of those zeros together to get 1,000,000. So this number is going to be 6. But if we think actually, why was it 6? Not just that's the number of zeros inside the million. Where that 6 came from is that we had 3 copies of that 100, and each of those 100 had 2 different zeros. See, that way it's a more general way you can think about it, where if instead of taking 100 cubed, we were looking at 1,000 cubed, or 1,000 to the n, or x to the power n, you can think that it's whatever that value of n was, the number of copies we were multiplying in, times the number of, well, let's see, it's not x, times the number of zeros that were in whatever we substituted for x, which in this case was 100. So if instead I had taken something like log of 10,000 to the power n, this would be the same as taking n copies of that 10,000, counting the number of zeros in each one of them, which is 4. So it would be n times 4. And of course, the general property that most of you correctly answered is that you have this lovely little effect where when you see the log of something raised to a power, that little power hops down in front of it, and you just have log of what was on the inside. Now, one of the maybe most important implications of that, I don't know if you'd call it an implication or if you'd call it a restatement of the definition. If I'm taking log, and I'll just reemphasize it's base 10, of 10 to the power n, we can kind of think of that little n as hopping down in front, and it becomes n times the log base 10 of 10, which is of course 1. This expression you can think of as either counting the number of zeros at the end, or more generally, it's asking 10 to the what equals 10. And the answer is simply 1. Which is very reassuring, because another way that you could go back and just read this original expression is saying 10 to the what equals 10 to the n. Oh, well, the answer is n. Okay? Now, with every given logarithm property that we have, so in this case we just found one, log of x to the power n involves that n hopping in front, there's always going to be a mirror image exponential property. And that's another way that we can hope to get ourselves a little bit of intuition for these. So let me just cover up some of the future properties we're going to get to here. Try to hide where we're going. What we just found, raising something to the n that hops in front, this corresponds to the exponential property that if I take 10 to the x and raise that whole thing to the power n, that's the same as taking 10 to the n times x. And this gets us to another intuition that you might have for logarithms, which is they're like exponentiation turned inside out. And here's what I mean by that. The thing sitting on the inside of the log, if I'm taking log of a, you should be thinking of that as the whole outer expression for something that's exponential. In this case, the a, the thing on the inside, corresponds to 10 to the x, the output of the function. Whereas the entire thing itself, the log of a, corresponds to what's on the inside over here, just what's the exponent of the 10. So wherever you see a log expression here, you should be thinking that plays the role of an exponent on the right side. And every time you see a exponential, the entire 10 to the x expression, the whole outer component on the right side, that corresponds to something that's sitting on the inside of one of the logs. Okay? And we saw this above, right? The idea that when we're multiplying on the inside, that's adding on the outside. Well, if logs kind of turn exponentials inside out, that's telling us that multiplying on the outside, multiplying the outputs of the function, is the same as adding on the inside. Because each of these logs, like log a and log b, is playing the role of the x and the y in the expression on the right. Okay. So with that, let's keep playing. Let's just do a couple more of these and see how many of these properties that we can build up an intuition for. So this last one, very nice, thinking of exponents hopping down. The next one is something that might look a little bit weird to those who are not necessarily familiar with logarithms. But again, plug in some numbers to gain some intuition for it. And we'll give it a little bit a moment to pull up which of the following is true. Log base a of b is negative log base b of a. Okay. Log base a of b is 1 divided by log base b of a. Log base a of b is 1 minus log base b of a. Log base b of a is log base a of 1 divided by b, or none of the above. So it's asking what happens when we swap the base with what's sitting inside of the logarithm. And I'll just give you a minute or two to answer that. Okay, so it seems like answers have kind of stabilized out there, so let's go ahead and grade things. And in this case, the correct answer of the choices we have comes out to be B, that the log base a of b involves taking 1 divided by the log base b of a. Again, let's think this through both in terms of an example and then in terms of a more proofy, systematic reason why it should be true. So if we're swapping our bases, let's just start off with, I don't know, our good old friend log base 10, and let's plug in a nice power of 10 like 1,000. Counting the number of zeros, we get 3. So let's try swapping the bases and see what this should mean. Log base 1,000 of 10. Okay, well, what is this asking, right? Maybe you think of drawing the little triangle, saying something like, we know 1,000 to something is equal to 10. 1,000 to the what equals 10? Well, if 10 cubed is 1,000, that is the same thing as saying 10 is equal to 1,000 raised to the 1/3. Doing the inverse here involves the multiplicative inverse of the exponent. And the way that pans out is that it looks like 1 divided by 3. And that 3 corresponds to the log base 10 of 1,000. It's 1 divided by the log base 10 of 1,000. So more generally, you might guess, based on this single example, that when we swap the base with what's on the inside, it corresponds to taking 1 divided by what's on the outside there. And again, you can think this through in terms of looking at the corresponding exponential rule. Now what happened to my lovely little log and exponentials. Wonderful. So, again, let's hide where some of the other properties that we'll get to here. And I'll keep it in the same order I had it before. Here I was thinking that having it pre-written could keep me a little bit cleaner than usual, but maybe it just involves playing this weird game of paper cutting, shuffling around. All right, so what we just found, log base b of a, if you swap those, it's the same as dividing by 1. What this corresponds to, off in exponential land, is if you take b to some power and say that that equals a, that's the same statement as saying that a to the inverse of that power equals b. Again, it's kind of helpful to take a moment and think of the logarithms as turning things inside out. The expression log base b of a is playing the role of that x, okay? And the expression log base a of b is playing the role of whatever sits on top of the a, okay? And then symmetrically, the whole expression b to the power x is playing the role of the inside on the left. It plays the role of the a. And the whole expression, a to the power of something, plays the role of what's sitting inside the log base a there. So you can see, just by plugging in some examples and by corresponding it to the exponential rules, we can already think through 3 different logarithm rules, which if they were just handed down as pieces of algebra to be memorized, you could memorize them, but it's very easy for them to kind of slip out of your head. And it's also very easy to get frustrated by the task at hand. But you might want to remind yourself that the reason we care about these sorts of things is understanding the rules of logarithms helps us do math in contexts where it's like a virus growing, where from one day to the next, from one step to the next, things tend to grow multiplicatively. Understanding the rules of logarithms helps you to get a better feel for that kind of stuff. So before we do a nice real-world example of what that can look like, let me just do one more quiz question in this vein to ask about properties of logarithms. Okay? One last one before we transition to a little bit of a real-world example. Get rid of what we had here. And now, which of the following is true? Log of a plus b is the same as log of a plus log of b. Log of a plus b is equal to log of a times log of b. Log of a plus b is equal to 1 divided by log of a plus log of b. Or log of a plus b is equal to 1 divided by log of a times log of b, or none of the above. Ah, and now we don't have as much consensus, do we? Very interesting. We've got a horse race between 2. So I will give you a moment to think this through. While people are answering, actually, I have a little question for the audience. So, I was just talking about how we might think in terms of multiplicative growth. And that doesn't just have to be powers of 10. We could also do something like powers of 3, where if you're going from 1 to 3 to 9 to 27 to 81, all of these, we could say that the log base 3 of these numbers just grows in nice little steps. So log base 3 of 1, 3 to the what equals 1? The answer is 0. In general, the log of 1, no matter the base, will be 0. Log base 3 of 3, 3 to the what equals 3 is 1. Similarly, log base 3 of 9 is 2. You might wonder what my question is, but it'll help to draw all of these out. And for my own pleasure here, let me just write out one more. Log base 3 of 81 is 4. Now, I've heard that ostensibly, if you ask a child, let's say around like 5 or 6 years old, what number is halfway between 1 and 9? Okay, you say, what number is halfway? Their instincts for how to answer are logarithmic, whereas our instincts tend to be more linear. So we often think 1 and 9, you've got a bunch of evenly spaced numbers between them, 2, 3, 4, 5, 6, 7, 8. And if you go right halfway in between, you'll land on 5. But if you're thinking in terms of multiplicative growth, where to get from 1 to 9, it's not a matter of adding a bunch of things, but you're growing by a certain amount. You grow by a factor of 3, then you grow by another factor of 3. Supposedly, a kid's natural instinct lines up with saying 3. And supposedly this also lines up with if you have anthropologists studying societies that haven't developed counting systems and writing in the same way that modern societies have, they'll answer 3 for this. So my question for the audience, if any of you watching right now have access to a small child, let's say in the range of 5 years old, see if you can go ask them what number is halfway between 1 and 9. And if you can, let us know on Twitter what the child says, what their actual answer is. Because I don't know why. I'm just a little bit skeptical of whether that actually pans out in practice. I understand this is not a super scientific way to do it, asking people watching a YouTube live stream to survey their own children and then tweet the answer. But for my own sake, it would be interesting to see some kind of validation there. Back to our question. This is the first one that doesn't seem to have a huge consensus in one direction. But let's go ahead and grade it to see what the answer turns out to be. Great. Okay, so 2,400 of you correctly answered that it's none of the above. Okay, that log of a plus b doesn't satisfy any of these nice properties. And in general, unless we're going to be working with certain kinds of approximations, especially when the natural log comes into play, we might talk about this next time, adding the inputs of a logarithm is actually a very weird sensation. It's a very weird thing to do. And to get a sense of that weirdness, plug in some powers of 10. Right? If I ask you log of a plus b, what you might start thinking is, okay, let me just plug in some examples, like 10,000 and 100. And I ask myself, if I do this zero counting function of what's in that input, how many zeros are in it? But it's weird, because when we add 10,100, well, we're no longer at a clean power of 10. And okay, that's fine. You know, often you're taking logarithms of things that aren't clean powers of 10. But it becomes very strange to ask how you express this in terms of log of 100, which was 2, and log of 10,000, which was 4. Because if you look at log of 10,100, it's asking 10 to the what is equal to 10,100. You might say, I don't know, it's going to be a little above 4 because it's kind of close to 10,000. So the best you might guess here is, oh, this is going to be something that's kind of like the log of 10,000. But that just feels like a coincidence based on the two numbers that we happened to put in. There's not a nice systematic reason coming there. So maybe you guess, oh, if the numbers a and b are very different, it's kind of close to whatever the maximum of them is. But it's very bizarre. And most importantly, for the sake of the quiz, if you just look at the options that it's giving you, if you try this out with any particular numbers, you'll find that none of those actually work. So all is good. Sometimes you get something that looks like it's going to be a nice property, but it doesn't end up being a nice property. And I also think that's important. Rather than just finding yourself only working with the various, log of a times b, or log of x to the power n, these things that have a nice rule. Sometimes you're out in the mathematical wild, you're working on some problem, you have a logarithm expression, and it's adding things in the input, and you want to be able to have familiarity with the fact that that's kind of weird, that you're not going to be able to simplify. But if you hadn't thought about that before, you might wonder, oh, is there just some formula that I haven't seen before? So with all of that, let me go ahead and take a couple questions from the audience before we transition to a different sort of example. So it looks like Uma Sharma asks, can the base be 0? That's an interesting question. Okay, can the base of a logarithm be 0? Well, in terms of our triangle, we might think of that as saying, 0 to some kind of power x is equal to some other value y, right? This is something that we could write either by saying 0 to the x equals y, or we could write the same thing by saying log base 0 of y is equal to x. 0 to the what equals x. Now the issue here is that 0 to anything ends up being 0, right? So if we're just going to be thinking of log base 0 of y for any other input y, you want to input something like 1 or 2 or pi, anything you might want, you're asking the question, 0 to the what is equal to 1 or 2 or pi or whatever number you might have there. And there's just not going to be an answer. So at best, you could try to say, oh yes, log of 0, it's a perfectly valid function. It's only defined on the input 0. But even then, you'd have trouble trying to finagle what you want there, because saying 0 to the what equals 0, it's like anything applies to it. So your arm is going to be twisted behind your back, however you want to make that work. And it corresponds to the fact that the exponential function with base 0 is entirely 0. It doesn't map numbers in a nice one-to-one fashion onto each other. So that's a great question. Can you have a log base 0? Now, back to the idea of where these things come up in the real world. One example I kind of like is the Richter scale for earthquakes. So the Richter scale gives us a quantification for how strong an earthquake is. Okay? And it can be anything from very small numbers up to very large numbers. Like I think the largest earthquake ever measured, and this is just a chart that comes from Wikipedia, was a 9.5. Okay? And to appreciate just how insane that is, it's worth looking at the relationship between what these numbers mean and then something like the equivalent amount of TNT, some sort of measure of how much energy there is in it. And then what we can try to do here is see if we can get an expression for the Richter scale number in terms of the amount of energy, and why logarithms would be a natural way to describe this. So the key to focus on is, as we're taking steps forward, how much do things increase? So for example, if we go from 2, well in this case it doesn't show us where 3 is, so maybe we think of taking a step from 2 up to 4, which is kind of like taking 2 steps. What does that do in terms of the amount of energy? Well, it looks like it takes us from 1 metric ton of TNT, which is, I guess, a large bomb from World War II, and it takes us up to a kiloton, 1,000 times as much, okay, which is a small atom bomb. So just 2 steps on the Richter scale, going from an earthquake of magnitude 2 to an earthquake of magnitude 4, takes us from large bomb from World War II up to the nuclear age, right? So that is noteworthy. And the first clean step that we get is going from 4 to 5, at least in terms of what this chart is nicely showing us. And evidently a single step up from 4 to 5 corresponds to going from 1 kiloton to 32 kilotons, right? And that was evidently the size of the city-destroying bomb that landed on Nagasaki. So this is maybe one thing that can be counterintuitive about logarithmic scales. If you're just hearing in the news the difference between, oh, there was an earthquake that was a 4.0 versus an earthquake that was a 5.0, it's easy to think, yeah, 4 and 5, those are pretty similar numbers. But evidently, in terms of TNT amounts, that corresponds to multiplying by 32 to get from one to the next. And going from 2 to 4 was evidently multiplying by about 1,000. Okay? And the only reason that's bigger is because here our chart wasn't showing what 3 was, so we were taking 2 steps. And you can verify for yourself that if you take a step of 32 and then you multiply by another 32, that's actually pretty close to 1,000. So the idea that additive steps on the Richter number correspond to multiplicative steps in the TNT seems to suggest that something logarithmic is at play here. And it's a little interesting to just keep going here and say, how much does this grow? Partly because of the world phenomena it's describing. Yes, not a huge surprise that as we take another step, it's multiplying by about 32 again. But reining that in to our intuitions, that's the difference between 32 kilotons, a small atom bomb, and then 1 megaton, which we might think of as, not small atom bomb, Nagasaki atom bomb, which I guess is 32 of the Nagasaki atom bombs for 1 megaton. That is evidently the magnitude of the double spring flat earthquake in Nevada, USA in 1994. I didn't know what that was. Thanks, Wikipedia. In terms of frequencies, by the way, I also looked these up. Evidently ones that are less than 2, those happen all the time. There's like 8,000 of those per day. But as soon as we're in the realm of atom bombs, things like 3.5 and 4, those evidently also happen quite frequently somewhere on the Earth. There's around 134 of those happening somewhere every day. Who knew? But as we get even more intense into this 5 and 6 range, which, you know, we're well above the atom bomb scale, now, we're only merely at around 2 per day. And you know, I'm sure that a geologist could come in and explain why we all shouldn't be super worried about the fact that there's 2 atom bomb equivalent disruptions to the Earth's crust happening every day. But presumably it's particularly rare for those to be concentrated on some spot, like a city where lots of people live. Now, just verifying that our thought that each step involves a growth of 32, let's look at what the step from 6 up to 7 looks like. And here it's giving us lots more examples in between, maybe giving the illusion that that's a bigger step than it actually is. And indeed, that's the difference between 1 megaton and 32 megatons. So that's multiplying by 32. One of the things I found most interesting on this chart, by the way, was look at how far we have to go before we get to the largest nuclear weapon that's ever actually been tested. This was height of the Cold War, the Tsar bomb, that was 50 megatons. And I believe they actually had original plans to have a 100 megaton bomb, but talked themselves down from that. 50 megatons, we're talking, start off at that 32 kilotons of the Nagasaki bomb, multiply by 32 to get a megaton, multiply by another 32, right? So we're talking about 1,000 times the strength of the World War II ending explosion. And you're still not at the 50 megatons of what humanity is capable of. And that is evidently, the Java earthquake of Indonesia. So 7.0 is not just a little bit bigger than 6.0, it's a lot bigger. And the point here, of course, is just that when you have a scale giving you multiplicative increases, it's worth appreciating that what look like small steps can actually be huge steps in terms of the energy implied, or the absolute values implied here. When we're thinking about the fact that there was ever a 9.5, that actually seems absurd, given that it's only in the 7.0 range that we're talking about the largest thermonuclear weapon ever put out. And this is indicative of one area where logarithms tend to come about. It's when humans want to create a scale for something that accounts for a hugely wide variance in how big things can be. So in the case of size of earthquakes, you can have things from what happens just all the time around the Earth, the size of a large hand grenade, and you want that to be on your scale and something to think about, ranging all the way up to the largest disruption that we've seen in human history, right? And in order to have that in a way that you're not just writing a whole bunch of different digits in your numbers for one case and a smaller number of digits for your number in another case, it's nice to take logarithms and then just put that on a single scale that basically squishes those numbers between 0 and 10. You see something very similar going on with the decibel scale for music. That one actually works a little bit differently, where every time you take a step up of 10 decibels, that corresponds to multiplying by 10. So rather than a step of 1 multiplying by 10, it's a step of 10 that multiplies by 10. So that kind of makes the math of it a little bit screwy. But the idea is the same, that if you're listening to a sound that's 50 decibels versus 60 decibels, it's a lot quieter in terms of the energy being transmitted. And going from, what would it be, 60 to 70 or 70 to 80, those steps, from 60 up to 80, that involves multiplying the amount of energy per square area by a factor of 100. So every time you see a logarithmic scale, know in your mind that that means whatever it's referring to under the hood grows by a huge amount. This is, again, why we saw a lot of logarithmic scales used to describe the coronavirus outbreak. So, how might you describe a relationship like this, where every time you grow the Richter scale number by 1, you're multiplying by 32? Well, we could think in terms of a log with base 32. I could say if I take the log of, I'm just going to call r the number for the Richter scale, I might think of this as log base 32. And that's going to correspond to, no, I'm doing this wrong. No. That's not the thing that's logged. We take the log base 32 of the big number, of the TNT number, something that was like, 1 gigaton or 1 megaton. It's 1 million tons. The log base 32, that should correspond to the Richter scale number. But there might be some kind of offset. So we might say that there's some kind of constant s that we're adding to this Richter scale number. And this expression is exactly the same, excuse me for going off the bottom there, this expression is exactly the same as saying 32 to the power of some offset times our Richter scale number, which is the same as taking, 32 to that offset, which itself is just some big constant, times 32 to the Richter scale number. So you might think of this as just being some constant times 32 to the power of the number you see. So this way of writing it really emphasizes the exponential growth of it, that if this is what corresponds to the TNT amount that you see, as you increase that r step by step, you're multiplying by 32. But another way of communicating the exact same fact is to take the log base 32 of whatever that amount is. All right, now the next thing I want to talk about is how we don't always have to worry about how to compute logs of different bases. You know, it's a little weird here that we were talking about log base 32. I referenced earlier how mathematicians really like to have a log with base e, computer scientists really like to have a log with base 2. And it turns out, for computational purposes, or for also thinking about how these things grow, if you have one log, if you're able to compute one type of log, whether that's base 10, base 2, base e, you can compute pretty much anything else that you want. Okay? Now, to get our intuitions in that direction, let's turn back to our quiz and go to the next question. And I believe that this question is the most, oh no, this is a halfway reasonable question. This should be nice. This is just going to get us prepared to translate from base 2 contexts to base 10 contexts. And it's also a good intuition for understanding powers of 2 to have in general, the relationship that it has with powers of 10, because it's this lovely kind of coincidence of nature that these two sort of, well, you'll see what I mean. They play nicely with each other. So our question asks, given the fact that 2 to the 10th is 1024, 1024, which is approximately 1000. Okay, so you can, if you're being a little bit loose with your numbers and you're just making approximations, 2 to the 10th, basically 1000. Which of the following is closest to being true? Log base 2 of 10 is approximately 0.3. Log base 2 of 10 is approximately, log base 10 of 2 is approximately 0.3. Log base 2 of 10 is approximately 1/3, or log base 10 of 2 is approximately 1/3. Okay, which of these is closest to being true based on the fact that 2 to the 10th is essentially 1000? I'll give you a little moment for that. Interesting that we've got kind of a split on this one. So I'm wondering if they're going to be numerically pretty similar, or if they're going to be conceptually similar, or if there's even a difference between those two. So since answers keep rolling in, I'm going to give this a little bit more time. So anyone at home watching, hopefully you already have a pencil and paper out to be noodling through these yourself. That is the spirit of the lectures that we're doing. If you don't, now is the time to take out a pencil and paper and see if you can think this one through and write it out. Some of the problems that we're going to build to here definitely will require pencil and paper, so now is as good a time as any. And if you're watching this in the future, even if you can't participate in the live poll, I really do think it's a lot of fun to kind of throw your own hat into the mix, even if it's not going to contribute to one of the numbers that you see growing on the screen. Give you a little bit more time here as the answers seem to continue rolling in. Okay, so I'll go ahead and grade it now, and let's see how people did on this one. So the correct answer is B, which is that the log base 10 of 2 is approximately 0.3, and it looks like 1850 of you correctly got that, so congratulations. But the close contender, not at all a unanimous decision here, looks like it was D, which is that the log base 10 of 2 is around 1/3. So that's good. They're very numerically similar, right? That it's either 0.3 or around 1/3, which is 0.3333 repeating. But the question was asking which one is closest to being true. And let's see how we can think about this. So it points out that you have a power of 2, which is 1024, awfully close to a power of 10, about 10 cubed. And the question is how we can leverage this to understand something like log base 2 of 10, or log base 10 of 2. As we saw earlier, those are just the reciprocals of each other. So what does this mean? If log base 2 of 10 is equal to x, that's the same thing as saying 2 to the x is equal to 10, right? It's asking us 2 to the what equals 10. So what we have here is an expression 10 cubed is approximately equal to 2 to the 10th. So what I might write out is we know that 2 to the 10th. Instead of writing it as a 10, I'm going to write that 10 as 2 to the x, where x is the number such that 2 to the x is equal to 10. So if that cubed is the same as 2 to the 10th, this is, I'll just write out the full details, the same as saying 2 to the 3x is equal to 2 to the 10th. And exponentiation is a nice one-to-one function, so it's okay to just say whatever's going on in the input, if the outputs are the same, the inputs must also be the same. You can't do that with every function. People seem to think you can do that with any function, but you just can't. And what that means is that x is about 10/3, okay? Great, so log base 2 of 10 is about 10/3. So if we looked at our answers though, that's not actually any of the options. We've got various things asking log base 2 of 10 being around 0.3 or 1/3. So it looks like instead we should try to re-express this as log base 10 of 2. And well enough, what we saw earlier is that log base 2 of 10, we could also say log base 10 of 2 is just 1 over that amount, 1 over x. And you can see this pretty easily by writing 2 is equal to 10 to the 1 over x. If we're asking 10 to the what equals 2, the answer is 1 over what we just got there. So log base 10 of 2 is 1 divided by this amount, which is 3/10, which is 0.3. Great. So this is kind of a nice constant to think about because there's this wonderful pattern that happens when we're looking at powers of 2. So if I ask, what is the log base 2 of 1,000? Like we just saw, it's approximately the case that 2 to the power 10 is equal to 1,000. And because we're doing things in logs, I'm just going to be writing it in that way. A log 2 of 1,000 is approximately 10. Similarly, log base 2 of 1,000,000, well, let's see, if we have to multiply 2 by itself about 10 times to get to 1,000, we should have to multiply it by itself around 20 times to get up to 1,000,000. And indeed, log base 2 of 1,000,000 is approximately 20. It's a little bit smaller, but this is kind of a nice approximation to have in your mind. And then similarly, you'll see why I'm writing out this as a pattern in just a moment. If we wanted to go up to 1,000,000,000, saying how many times do I have to multiply 2 by itself to get to 1,000,000,000, this is about 30. And any computer scientist out there who's thought about, just how much is a kilobyte or a megabyte or a gigabyte, they'll be familiar with the idea that powers of 2 are nice and close to these powers of 10, or more specifically, powers of 1,000. Now, what I want to do is just write all of the same things with log base 10, not approximately equal to, this is actually equal to 3. Log base 10 of 1,000 is equal to 3. Log base 10, well, you tell me, what's log base 10 of 1,000,000? It's counting the number of zeros, it ends up being about 6. And log base 10 of 1,000,000,000, counting the number of zeros, it ends up being 9. Now, the reason I wanted to write all of this out is to just emphasize an interesting pattern here, which is we're just growing by these increments, right? As we go from 1,000 to 1,000,000 to 1,000,000,000 with log base 2, we're stepping up by steps of 10. But when we're playing the same game with 10, we're stepping up by these increments of 3. So there's this nice relationship. And in fact, for all of them, to go from log base 2 to log base 10, it seems like we're just multiplying by 0.3. So 10 times 0.3 is 3. 20, we scale down by that same amount. 30, we scale down by that same amount. Okay? Now this is an intuition worth remembering. If you have your numbers described with one base, it's basically the same as describing them with another base, but there's some rescaling constant. Okay? Now the next question is going to start getting us at that direction, but it's going to be framed in a way that just looks like a whole pile of algebra. And again, I will encourage you to plug in numbers if you want to gain a little intuition for it. So as our third to last question, this will be a long lecture, we have which of the following is true? And then just a whole pile of various possible ways to combine log base c of b times log base c of a. Does that equal log base b of a? And rather than me reading them out to you, I'll just let you look through them, plug in some numbers. I'll give you meaningful time on this one because it's not obvious unless you're already familiar with logarithms, and it's worth thinking through a little bit. We have an outstanding question from the audience, which is, does the bar length of the pole use some kind of log function? And helpfully, it looks like Ben Eater has gone ahead and directly answered in the form of the code involved, where the chart max is raising 2 to the power of a ceiling of a log base 2 of the maximum attempt count, which I think is to say unraveling. If you're looking at the maximum number, I'm not great at Vanna Whiting this thing. If you look at the maximum number in our poll, it's asking what's the log base 2 of that. So as it crosses different powers of 2, then that rescales it. And yes is the answer. What a fantastically apropos question. Thank you, Karen. All right, so answers are still rolling in, and I think, like I said, I just want to give you some more time to think this through because it looks like a big pile of algebra. Plug in some numbers to see what seems to work well and see which answer fits. Okay, so even if you are still thinking about it, I'm going to go ahead and grade it here and then start talking about why it's true, and then also why we should care, why this is an operation that actually tells us something. So the correct answer, which it looks like around 1,700 of you got, congratulations, is log base c of b times log base b of a is equal to log base c of a. Great. Now that's just a big old pile of things. Why would that be true? How do we think about it? Now, phase one, like I said, we might plug in an example, but let's try to actually think about why the example holds. So let me pull out. We've got this as one more of the log rules. This is just repeating what the correct answer turned out to be, where we've got an expression for log base c of b, log base b of a, and this ends up being log base c of a. It's gotten rid of the b's, which is kind of interesting. So some examples you might plug in here would be things like, let's use a different color. Let's use green. Instead of c, I'm going to go ahead and plug in 10. Log base 10 of 100, which is kind of asking how many times does 10 go into 100 in a multiplicative sense? How many times do I multiply 10 by itself to get to 100? Where the answer is 2. And then log of 100 of, let's plug in another power of 10. It'll be nice if it's also a power of 100. So I'll do 1,000,000. So this one is asking 100 to the what equals a million. How many times do I multiply 100 by itself to get to a million? How many times does 100 go into a million? Phrasing the same thing 10 different ways. Now, the claim is that this is the same thing as taking log base 10 of a million. That if I ask how many times does 10 go into 100, and how many times does 100 go into a million, multiplying those should give me the answer to how many times 10 goes into a million. Now, just checking the numbers, this certainly works. 10 goes into 100 2 times. 100 goes into a million 3 times in a multiplicative sense, in that 100 cubed is equal to a million. And indeed, how many times does 10 go into a million? Well, 6. Now we could think of this property in terms of the corresponding exponent rule, which is going to look a little bit stranger, but it's actually just saying entirely the same thing. So here, if we have a base of c and a base of b, and we're trying to relate those to each other, the whole statement is equal to saying that, suppose that b to the x is equal to a. Got some number b, you raise it to some number x, and it equals a. Suppose it's also the case that c to the y equals b. Those two together are the same as saying c to the xy equals a. Now, that's kind of a mouthful to say out loud, but if you plug in some numbers to translate what all of that is really saying in the context of the example we just did, we're saying if you can write 100 as 10 squared, and if you can write a million as 100 cubed, well, that lets you write a million in terms of a power of 10. Okay? So sort of asking this question, how many times does one number go into another, but letting you layer it on top of each other. Now, if we rearrange that expression, we get what is probably the second most important of all of our log rules. The most important is this top one, that when you multiply the inputs, you add the outputs. But the second most important, which is known as the change of base formula, lets us write that if you want the log base b of some value a, then for whatever c you want, it doesn't actually matter what log you have in your pocket. If you use that other log, and you take the log c of a, divided by the log c of b, that gives you log base b of a. Okay, so just as an example here, what this would look like is, let's say I wanted to be able to compute log base 100 of things. I just really want to. It's not a button on my calculator, but I would love to be able to do it. And I want to do it with an input like a million. Well, even if I don't have the log base 100 button on my calculator, what I can do is say, I'll use the log base 10 button and evaluate what's on the inside here, which, at least positionally, it's kind of above the 100. It has a higher altitude as we write it. So this can line up with the notation a little bit, that it sits on the numerator. And on the bottom, I use the log base 10 button that's in my calculator on the base, on the 100. And then I can evaluate both of those and it'll give me the answer. In this case, it gets you 6 divided by 2, which will be 3. And if we really just think through what this is saying, I know I've said it many different times, but it's a convoluted enough way to write things, but an intuitive enough fact that I think just coming at it from a bunch of different angles can be important. Because like I said, this is probably the second most important log rule. We're asking how many times does 100 go into a million? In a multiplicative sense. How many times do I multiply by itself? But division is asking that same question in an additive sense. If I say how many times does the log of 100 go into the log of a million, that's what division means. It's saying how many times do I add this bottom number to itself to get to the top. But anything additive in the logarithm realm is the same as anything multiplicative in terms of what's inside the parentheses. So both of the left-hand side and the right-hand side are just saying how many times does 100 go into a million, but going about that in different ways. So this is extremely nice because it actually lets us compute things. Next time we're going to talk all about the natural logarithm, which is log base e, often written ln. And turns out this is much easier to compute. There's nice math behind it such that if you want to come up with an algorithm that your calculator can use, it's actually a lot easier to think of log base e of numbers. So anytime that you need to go to some kind of calculator, I don't know, let's say we popped over to something like Desmos, always happy to have as a friend, and you wanted to compute log base 10 of some number, let's say we're doing log base 10 of 57, and it looks like that's, it should make sense it's between 1 and 2 because 57 was between 10 and 100. What's going on under the hood? How is it actually figuring this out? It's going to use somewhere in there a change of base formula, which is going to be that the natural log of 57 divided by the natural log of 10 is the same thing. These are two different ways of writing it. So if you know one logarithm, you know all of the logarithms. Okay? And well, let's just use that fact to answer one more of our quiz questions. This will be the second to last quiz question. So thank you all for sticking it through. I think we will be, I think you'll be pleased by the last question, because the last question will actually be like a fun problem-solving puzzly thing, and it'll involve a lot of what we've used up to this point, kind of a culminating thing. So before that though, just to make sure that we've got the instincts of change of base down, what do we have? Use the approximation that log base 2 of 10 is around 10/3. So using that approximation, which of the following is approximately true? Log base 2 of x is about 10/3 of log base 10 of x. Log base 2 of x is log base 10 of 10/3 of x. Log base 2 of x is log base 10 of x to the power 10/3, or log base 2 of x is 10/3 times the log base 10 of x. And finally, none of the above. So I'll give you a moment to think about that. You might want to think to the chart that we were drawing earlier and thinking about log base 2 and log base 10 as we're looking at powers of 1000 and how each of those grows. That can leverage some of the intuition. But I'll let you think about it. Stop talking. While answers are rolling in, it looks like a number of people have been asking on Twitter about basically how complex numbers play into this. So we've got Jamul asking, what if the base is imaginary? We've got Kelkun asking, what about complex bases? Since z to the x is walking around a spiral, wouldn't it hit every complex number? Well, it won't hit every complex number, but your instinct that it's hitting multiple things is pretty spot on. Does it make sense to talk about logs with imaginary numbers by Nitya? So to all of these questions, it's actually a very nuanced question. The short answer is yes, complex logarithms absolutely exist, but each one of them has multiple different outputs. So a good analogy here is how if we have the square root function, if I ask something like the square root of 5, we have the convention that you always do the positive amount, but that doesn't quite feel honest. It feels like the right answer is to specify that there's two different outputs for the square root function, two solutions to x squared equals 25. And this is actually true in complex numbers as well. One of the things we talked about in a complex number lecture was that you can take the square root of I, and you actually get root 2 over 2 plus root 2 over 2i, but that there's two solutions. You can do plus or minus this value. And so you could say that the square root function isn't a function, but it's a multi-valued function. It always has two different outputs. Now something funky happens when we have exponents at play. So if you're just like someone who hasn't seen this stuff, don't worry, we talked about it in previous lectures. I'm obviously jumping around on the complexity level a lot here, where if in lecture 5 I'm talking about like Euler's formula with complex numbers and compound interest and like how that plays into physics. And then lecture 6, we're back to the basics of logarithms. I acknowledge that might be a little bit jarring to potential audience members. But just continuing on with the answer, if you note that e to the 2 pi times some number times I, this basically walks you around a circle so that the output will walk around a circle and just keep repeating. As n goes from 0 up to 1, it'll walk around one cycle and end up back where you started. As n goes from 1 to 2, you'll end up back where you started. So for example, e to the 0 sits here, e to the I pi is at -1, but e to the 2 pi I is also at 1. Same with same with e to the 4 pi I, that also equals 1. So in general, if you wanted to ask something like, what is the log base e of 1, on the one hand, we want to say the log base anything of 1 should be 0, because anything to the power 0 equals that 1. But if we're letting complex numbers into the mix, you would have to honestly say, well, 2 pi I is another pretty good answer to this question, because e to the 2 pi I also equals 1. And same with 4 pi I. And you could even go in the negative direction. And in general, n times pi times 2 times I, kind of wrote that in a weird order, for any integer n, feels like a valid answer to this question. So there's a couple ways that you can deal with that in math. And before we get back to our usual lesson just on logarithm rules, this is interesting enough, I kind of want to pull it up. Let's see if we have complex logarithm. Great. Wikipedia, always to our aid. Probably it'll have a nice visual of some kind for us. Ooh, look, such fancy color diagrams. What I want, okay, this is what I want. Wonderful. Let's zoom out a little bit. Great. So there's this notion of what's called a Riemann surface that's basically trying to capture the idea that you have a function with multiple outputs. And intuitively, maybe you can understand what it's getting at, where the input would be something on the xy plane, and the output, there's just many different outputs sitting there. So when you have a complex logarithm, you have to account for that. But it's actually a very useful idea to do, but it takes a lot more nuance than you might expect. So with all of that, hopefully that helped at least partially answer some of people's questions. Same by the way, with logarithms with base negative numbers, because if you're asking -1 to the x and really noodling on what that means, it gets you into the realm of complex numbers, so you have to deal with the same multiple output idea. Now, answers are rolling in more slowly, so this seems like a fine time to grade things. And the answer turns out to be, you rescale it. If you want to go from log base 2 of something to log base 10 of something, it involves rescaling. And one way you could think about this is with the change of base formula. So let's say we have, let's get rid of our e stuff. Let's say you have log base 2 of x, but we want to write it in terms of log base 10. We can write that as log base 10 of x divided by log base 10 of 2. Saying how many times does 2 go into x in a multiplicative sense is the same as saying how many times does the log of 2 go into the log of x in an additive sense. Okay? And, well, what is 1 divided by the log base 10 of 2? So we're going to keep our log base 10 of x out here. And from what we found earlier, we found that log base 10 of 2 was approximately 3/10, was approximately 0.3. So when we divide by it, that should get us 10/3. Okay? And this lines up with what we were looking at a little bit earlier with powers of 1,000. Let's see, where was it? Where was it? Great. So when we're converting from log base 10 of something up to log base 2, here we were thinking of multiplying the top by 0.3 to get to the bottom, but you could also think of multiplying by 10/3 to get to the top. Anytime you have log base 10 of some number, you just rescale it and you have log base 2 of that number. And the rescaling constant comes from the log base 2 of 10, or vice versa, log base 10 of 2. So that's change of base. Like I said, it's very important. It lets you put everything into a nice universal language. And that should be all of the hint that you need for the last question, which is a challenge question on this one. So if anyone's been watching and they've been like, I know logarithms, I've got this completely down. Let me pull up the last question, which came up on, let's see, it's not the AMC, but it's whatever the predecessor to the AMC was, I believe. So it's going to involve a little cleverness and manipulation. We've got this long sequence of fractions. Okay, you take 1 divided by the log base 2 of 100 factorial. And remember, 100 factorial is 100 times 99 times 98 all the way down to 1. So 1 divided by the log base 2 of that, plus 1 divided by the log base 3 of 100 factorial, plus 1 divided by log base 4 of 100 factorial, on and on and on, up until 1 divided by the log base 100 of 100 factorial. So this looks rather intimidating, right? Certainly adding fractions is never fun. Adding 100 fractions seems even worse. Dealing with a bunch of logs of different bases seems like a pain. And the factorial is playing into this. So I'm just going to give you, given that this is the wind down time, I'm going to give you 2 or 3 minutes to start thinking about this. And if you don't get it, it's totally fine. we're going to walk through what the answer is, but I'm just going to let people think about this final challenge question before we call it a day. So I'm going to give you a little bit more time on this one because it's definitely fun to work out, and I think if you know how to start, then great. But if you don't know how to start, just letting yourself kind of work with a couple of the different rules that we've worked out before. Change of base comes into play if you'd like to use that, and just kind of keep manipulating. And if it feels like you're getting something that's a little too messy, see if you come at it from a different angle. And because answers are rolling in a little bit more slowly now, what I'm going to do is just start to describe the explanation here and then come back to grade it in just a moment here. So the expression that we have looks like, I just started writing it out while you guys were working on it, 1 divided by log base 2 of 100 factorial, plus 1 divided by log base 3 of 100 factorial. And before you even start, the fact that the thing on the inside of the log involves a big product of stuff should actually feel good, because logs like to take in things that look like products because of the most important property that we have, which is the idea that it turns products into addition, okay? So right away you know that you're probably going to use that. Second thing you notice is that it's uncomfortable to have all of these different bases, log base 2 of something, log base 3 of something, log base 100 of something. So translating it all into the common language should be helpful. How does change of base work? Well, asking how many times does 2 go into 100 factorial is the same as asking how many times does the log of 2 divide into the log of 100 factorial. It doesn't even matter what logarithm you use. This log could be base 10, base e, base 2, doesn't matter. This change of base formula still holds. Now what that means for our expression is instead of taking 1 divided by log base 2 of 100 factorial, I could write that as log of 2 divided by, so let me draw a little dividing line between what I'm doing here, log of 2 divided by log of 100 factorial, okay? And then similarly, log of 3 divided by log of 100 factorial. So all I'm doing here is taking the reciprocal. So instead of taking log of 100 factorial over log of 2, I've inverted it, log of 2 over 100 factorial, because that's what this reciprocal is doing. So with that as the beginning, I'm going to go ahead and just grade this, lock in the answers, and see how everyone's doing. So it looks like, awesome. Around 1796, we always draw a little bit north of Ramanujan's number. Around 1800 of you answered that it's 1, which is correct. Congratulations. 70 of you answered 100, which we can maybe see where that error would have come from. Those of you that answered 0, that's interesting. It would imply that somehow you have cancellation at play because these are all positive numbers, so thinking one of them was negative. So you could probably gut check against the idea that it would be 0. 41 of you want me to come up with a number fun numerical fact about 69, but I won't. 28 of you said 2. And I think that's, I think the difference between 1 and 100 maybe would be interesting to try to analyze. But if we go back to our answer, I realize it's maybe a little bit confusing how I've written this. This is not a big fraction. This was just a dividing line between, ironically trying not to confuse my fractions with each other. So rewriting our expression up on the top here. As we add all of these things, and we can continue up until log of 100, all divided by log of 100 factorial. The key is that now all of the denominators are the same, so we can add the numerators. No more plus sign. This is just going to equal something. That top is going to look like log of 2 plus log of 3 plus on and on up to log of 100, all divided by the log of 100 factorial. And it seems like the only little contention among those answering the question is whether this should simplify to be 1 or should it simplify to be 100. And really the way we can think about this is to just break down that bottom part in terms of what a factorial means. I'll go ahead and do this on a bottom part since I didn't manage my paper real estate very effectively here. The log of 100 times 99 times 98 on and on times 2 times 1 is the same as adding all of them. And you can probably see this mostly cancels out with the top. The only question you might have, though, is that in the factorial, we keep multiplying down until we get that 1, which doesn't really make a difference. But before you think about it too much, you might wonder, hang on, on the bottom I'm multiplying everything and I'm adding this log of 1, but on the top, from what we found before, I never saw that log of 1. Does that make any difference? And the answer is no, because log of 1 is saying 10 to the power of what equals 1, and the answer is 0. So in fact, taking the log of 100 factorial is the same as adding the logs of all the numbers from 2 up to 100, and it simplifies down to 1. So to those of you who got it, congratulations. To those of you who feel like you maybe have better intuitions for change of base formulas, for the fact that logarithms turn multiplication into addition, that's my hope. In the next time, with this as a foundation of logarithms that can be pointed back to, what I would love to talk about is what's known as the natural logarithm, log base e, and try to give an instinct for why that's something that we care about. Okay? Why is it that mathematicians just seem to really love the number e sitting in the base of their logarithms? What does that buy for them? Why does it show up in nature? So that will happen on Friday at the same time as this lecture, and I look forward to seeing everyone there.